The DESI Data Release 2 results present the most precise baryon acoustic oscillation measurements to date. The survey mapped over 14 million galaxies and quasars across 11 billion years of cosmic history to test the limits of the standard cosmological model. That standard model assumes a constant vacuum energy. But when analyzing this new data, the results show a 2.8 to 4.2 sigma preference for dynamical dark energy, a force that changes over time. Specifically, the analysis suggests the dark energy equation of state, represented by the variable W, crosses the phantom divide of -1 at a redshift of roughly 0.5. Look at this contour plot. Standard two-parameter models process the DESI data by mapping the present value of dark energy, W0, against its evolution, WA. The resulting bounds push the trajectory decisively past the -1 threshold. This reading implies the universe is filled with exotic, evolving fields. But before we rewrite the physics, we must test the math itself. We have to determine if these specific mathematical tools are reading the data correctly, or if they are generating a mirage. Crossing that -1 threshold mathematically breaks standard single-field physics. To make a single-field model actually cross that line, you must introduce highly unstable, exotic field mechanics with negative kinetic energy. Furthermore, having this transition happen right in the middle of our observable window has been flagged by cosmologists as a substantial and unsettling coincidence. This points toward a structural error known as template bias. The hypothesis is that the standard two-parameter templates applied to this data are the wrong mathematical shape for the underlying geometry. When you force a complex cosmological history into restricted parameterizations, like the CPL or BA models, any physical behavior outside those limits gets projected onto the parameters you do have. This mismatch mathematically manufactures false features in the output. To test if the DESI anomaly is a mathematical artifact, we run a precise experiment. We construct a purely static, non-phantom universe where dark energy never evolves, and measure how standard templates attempt to read it. We establish our test baseline using mode identity theory. In this framework, the cosmos is a finite, static three-sphere geometry. Space itself does not physically expand. This maps the fundamental mechanism, a temporal standing wave pulsing along the perimeter. As it oscillates, variable S, the amplitude manifesting as matter, grows from 0 to 1. Redshift is strictly a ratio of phase positions, the observer's current phase divided by that expanding matter fraction. The relationship between this phase time and our proper time is governed by a precise mathematical rate called the Waltz clock, defined as the derivative of t with respect to tau equals s to the -1/2. In the early universe, integrating this specific nonlinear temporal clock forces an apparent expansion metric that scales as 1 plus z to the power of 3/2. Squaring that expansion rate to calculate the energy density yields 1 plus z to the third power. This exactly reproduces the standard scaling of the matter-dominated era. A purely static geometry, measured by a nonlinear clock, perfectly mimics the physical expansion of matter. Our perspective along the standing wave is evolving. With the matter scaling mapped, we evaluate the vacuum. In this model, the cosmological constant, lambda, is an isolated geometric feature. Lambda is defined as the ground eigenvalue of the space's Mobius surface. Because it is topologically protected by the boundary conditions of the geometry, it is strictly constant. It cannot dynamically evolve. To test if this static vacuum can masquerade as dynamical dark energy, we use a diagnostic tool called the fiducial matter split. We subtract the expected matter scaling to isolate the effective dark energy equation of state, or WEFF. This equation maps the effective dark energy trajectory. Look at the numerator. For any redshift, it will always evaluate to 2 or higher. It is strictly positive. The denominator is definitively locked by the isolated constant, omega lambda. Because this additive constant is greater than 0, the entire lower half is also strictly positive. With both halves strictly positive, the total equation of state must remain greater than -1. A phantom crossing is structurally impossible. We now have a mathematically proven non-phantom universe. The test is to see how standard algorithms interpret it. We generate pure, noise-free baryon acoustic oscillation distances directly from this MIT math. We pin these generated observables to the exact 7 effective redshifts used by the DESI DR2 survey. This chart maps the true trajectory, never crossing the -1 threshold. We feed this data into standard 2-parameter templates. The templates attempt to bend to align with the data, but lacking the parameters to capture the true curvature, the algorithm absorbs the mismatch, forcing the residual down across the dotted -1 threshold. We can verify this error by analyzing the exact same data with a 3-parameter polynomial model, giving the math higher degrees of freedom. When given sufficient mathematical flexibility, the chi-squared error drops to near 0. The model fits the curve accurately, and the phantom crossing completely vanishes. We ran a threshold scan across the full spectrum of data-allowed observer phases. The 2-parameter templates generated an artificial phantom crossing in every single test. The dynamical dark energy anomaly is a basis restriction artifact. Limited mathematical tools force a static geometry to output the illusion of dynamical physics. The mock experiment isolates the template bias. Now we test the MIT baseline against actual astronomical observations, combining the Pantheon plus supernovae compilation with the true DESI DR2 measurements. We ran an MCMC joint fit, testing both standard flat ΛCDM and the phase clock model against 1,714 physical observables spanning cosmic history. This table details the statistical output. The critical metric is the delta chi-squared value, which comes out to positive 0.11. At equal parameter counts, this means the two models are statistically indistinguishable. The isolated supernovae and BAO rows show near-identical data splits. Current data fitted to constant W models does indicate a slight statistical departure from -1. However, the data does not require a phantom crossing to explain that departure. The phase clock model natively produces a trajectory strictly greater than -1, which aligns with that constant W drift. But at our current parameter constraints, the predicted deviation is too small to definitively isolate. Right now, a physically expanding universe and a static phase clock universe fit the observational data equally well. To break this degeneracy, we require a highly specific, falsifiable fingerprint. That fingerprint exists. The mathematical structure of the phase clock model predicts a unique, purely negative 1 plus z to the first power term, embedded directly in the Hubble rate. This table displays standard density scalings, radiation to the 4th, matter to the 3rd, curvature to the 2nd, and the cosmological constant to the 0 power. The phase clock correction sits exactly at the 1st power. Its magnitude is strictly tied to the observer's current phase. Based on the joint data fit, this correction alters the expansion rate at redshift 1 by less than 0.8%. That falls just underneath the 2 to 3% noise threshold of the current DESI measurements. To push below that threshold, we have to look to the next generation of hardware, the Euclid Space Telescope. The forecasted Euclid Data Release 2 will hit roughly 0.5% precision per bin. That provides enough resolution to register this specific phase clock scaling at 1.5 sigma per bin. These specific falsification parameters have been officially locked in and registered on Zenodo ahead of the upcoming Euclid data releases. Before we rewrite physics with unstable dark energy fields, we have to wait for the resolution to see the actual math. Euclid will confirm if the universe is physically tearing itself apart, or if we are merely misreading the temporal edge of a static, finite geometry.